I will begin with a word of prayer momentarily. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless our work today, Lord, as we prepare for test 3. Amen. All right. I graded your quiz 3 right before class. I actually came in yesterday to pick up tests to grade because I got back into town mid-morning, and then I had errands to do in the afternoon. But I forgot to pick up your quiz yesterday. As I get home last night, I was like, But then I just made a point to grade them during convo, and for that reason, the grading is so-so. As in, some of it is careful, and some of it is not so careful.
But we like generosity.
You like generosity? But I think it's in everyone's best interest, because rest assured, I will find time to carefully grade test 3 and the final. So, let's. Some of you probably got credit for something that if I had more time, I might have dinged you something, So let's talk a little bit about it. All right. So, well, first of all, I think you guys knew once you saw it that you should have been able to get this one, because this is like the first thing I did, I think, after the last test. Yeah, and we did it 2 different ways. And I don't know. I think about a third of you just destroyed this, just perfect, great. And I think maybe about 7 of you did the direct proof, kind of like I have here. And then 2 or 3 of you were successful in the contradiction style proof. And then the rest of you need to work on it. So any questions here? I mean, we need to start by assuming that we have eigenvectors with distinct eigenvalues. I forgot to give you that they're non-zero. That's yeah. But did I? No. Well, I didn't need to say that here because I said v1's an eigenvector. In contrast, problem 3, I needed to tell you that they were non-zero. And so I, take a linear combination equal to 0. I chose to multiply by a minus lambda 2 times I. When I do that, and I work out the algebra here, I get this times that v1, and over here these cancel out, so I just get c1 times the difference of the lambdas times v1 equal to 0. But the thing is, lambda 1 and lambda 2 are distinct, and v1's not equal to 0, which means that this is non-zero and that's non-zero. And early on we proved a lemma, or stated a proposition at least, that if you have a product of a scalar times a vector equal to 0, it must either be that the vector is 0 or the scalar is 0. So it means that this scalar has to be 0. But if this scalar is 0, it must be that c1 is 0, because lambda 1 minus lambda 2 is non-zero. So something like that. And then, of course, once you have that, then you go back to the original equation, knowing that c2 is 0. Excuse me, knowing that c1 is 0, you're able then to show that c2 is 0. Of course, you could have multiplied by a minus lambda 1I, in which case you'd have found that c2 was 0 first, and then you've gone back and shown that c1 is equal to 0. But one way or the other, the argument should include the complete thought process for why c1 and c2 are both 0, and hence we have linear independence of that set, or the corresponding contradiction proof, which we also went over in class. But any questions? So some of you studied too hard, and you converted my n equals 2 problem to an n equals n problem. Some of you had c1 v1 plus c2 v2 plus da 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 plus cn vn, and then you were doing that's a much harder problem. Don't do answer problem that's given. Another person made A a 2 by 2 matrix. Do not do this. This is not a 2 by 2 matrix. This was not given. And if you're going to try to do something related to this problem, but with a 2 by 2 matrix, you should tell me that's what you're doing, and you know that it's not a proper solution to the problem, to convince me that you know what you're doing, but are just seeking partial credit or something. Do take the time to write that sentence if you're going to do that sort of thing. All right. It is not important who did it. At least 5 of you have done this at some point in the semester. More so early on. yelling in the grading about this has, for the most part, discouraged you guys from continuing to do it. So, I think, or maybe, I don't know. Let's not speculate. There's no point in it. So this one here, I saw the wrong answers were very wrong here. The wrong answers were very, very wrong. You know, if you're trying to find a basis, an orthonormal basis for the space, this is a space of matrices, so your basis should be a subset of matrices. A lot of you have two-component vectors. I don't know what that is, but it's not a basis. Like a basis for a set of matrices should first be a set of matrices. Point number one. And then more than that, though, we want an orthonormal basis, right? So the idea is to take the set A, B, and run the Gram-Schmidt algorithm on it. It's really boring to start with because A is already a unit vector, so to speak, with respect to this notion of distance. So you could say that A is equal to A prime prime if you wanted to use my usual notation. But anyway, A is equal to its unit vector. So I can proceed with the Gram-Schmidt algorithm by subtracting off the part of B which is in the A direction, namely this. And when I do that, it gives me 0, 2, 2, 0. The trouble with B prime, of course, is that it has length square root of 8. So to fix it, I have to divide by the square root of 8, and there you go. That's a vector of length 1 in the 2 by 2 matrices. And this is the orthonormal basis which was wanted. I think about half of you got this. Like, many of you are pretty good on this. That gives me hope. So, questions, comments, conundrums? All right. Now, this is the problem I was probably most talking about. You know, I just grade. If you said yes, it's an isomorphism, I said, okay, great, great. I'm not even gonna look. You know, like if your reasoning was it's an isomorphism because it looks like it rhymes with schmorphism, I would have taken that. You know, I mean, I did not look at your reasoning, so it's entirely possible that your reasoning for why this was an isomorphism was fuzzy, vague at best. Now, and then the things that were wrongly written on this problem, again, they were very wrong. There's some things about, there's like some stacks of numbers and matrices. I have no earthly idea what you guys are writing. I just do not even know. But I was looking for the numbers 1, 4, and 9. If I found them somewhere and I could believe that you were saying that they were the eigenvalues for t squared, I was like, good. Because that's what they are. And here's the calculation that shows it. You don't need matrices or anything, right? We can just go straight to the definition, calculate t squared on v1, which gives us v1. T squared on v2 gives us 4v2. T squared on v3 gives us 9v3, which means that the eigenvalues are 1, 4, and 9 for t squared for the same eigenvectors. So the same vectors have different eigenvalues for t squared than they do for t. All right? But anyway, this much we can see. v1, v2, v3 is an eigenbasis. Now, the reason I know that is because what Dr. Sperano told you or wrote on your quiz, namely that v1 and v2 and v3 were non-zero. If I took that off, this answer would be more nuanced. Like, I could change this into a true, possible, false question, right? Same question, but true, possible, false, and you have to put possible, and then you'd say it is an eigenbasis if v1 and v2 and v3 are non-zero. But if one of them's zero, it's not a basis. So then it would be false. That would be like true, possible, false style question. But I wanted you to assume that they were non-zero. So I wanted that to be said explicitly. Sorry, I didn't in the original statement of the problem. Anyway, so once you know that this is an eigenbasis for t, that means that, I know that these are linearly independent. The reason I can say this is an eigenbasis is I know these are linearly independent because we know that they are, for t, right, eigenvalues 1, 2, and 3, those are distinct. So we know that distinct eigenspaces with the distinct eigenvalues are independent spaces, right? So in particular, if I take an eigenvector with eigenvalue 2 and an eigenvector with eigenvalue 3, put them together, that forms a linearly independent set, right? And the same for 3 things. You actually proved it for 2 things in the first problem, right? Some of you proved it for two things in the first problem. All of you will be able to prove it when that appears on the final, if it appears on the final. Let us be vague.
No, put it on the final.
Just put it on the final.
At least I know I'll get some points.
At least you know you'll get some points. You guys will all get some points. Don't be so negative. Let's see here. Points for your name. You definitely get less points if you don't put a name. If enough of you don't do that, then it becomes a problem at some point.
Also, fill out your surveys, please.
That's what I was going to ask. How do you know that we fill it out? Like, to get
The course evaluation, you said if we all fill it out, then we get extra credit.
Because I already did.
You already did?
I already did.
You already did?
Who hasn't? I want to call you out by name. I don't know any of your names.
Aha! This one. You need to work on this gentleman right here.
Sir, I need extra credit on my time.
She just sirred Ryan. It's not nice. Let's see here. I don't know. My experience, once a student starts saying sir this, sir that, it's like almost followed by a lie. I don't know. I don't know. It's like emails that you get. Sir, kindly your attention. I have this $1 million I'd like to put into your bank account. If you just, send me 10 or something or whatever it is, I'm a Nigerian prince, blah 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 blah. The usual. I always, if I'm bored, I always respond to these emails like, sure, first just send me $1. You send me the first $1, then we can go from there. They never respond though. It's disappointing. Anyway, so listen. Some way or another, we should argue that this is an eigenbasis. So, as I said, my argument was that it's an eigenbasis because these are distinct. And we know that eigenvectors with distinct eigenvalues are linearly independent. Okay? So I've got 3 linearly independent vectors. I was given that this is a 3-dimensional space. That means it's a basis. My solution would be even better if I wrote all that out. Right? So my solution's non-optimal. Like you could improve on my solution a little bit. So given that, the question then is T an isomorphism? Well, if we calculate the matrix of T with respect to this eigen, there's various ways to argue this, okay? One way you could argue would be that the kernel of T is non-zero. That would have been a lazier argument I could have made. Why would that be helpful? If we knew that the kernel of T was did I say non-zero? I meant the kernel of T is 0. Why do we know that the kernel of T is 0 here? If the kernel of T was non-zero, that would mean that 0 is an eigenvector. Excuse me, that 0 is an eigenvalue. 0 is distinct from 1, 2, and 3. So then we would have the eigenvector with eigenvalue 0, v1, v2, and v3 as a basis for v, which would be very troubling because that would be a set of 4 linearly independent vectors in a 3-dimensional space. If there's anything you leave this course knowing, you should leave this course knowing that that cannot be done. All right? So that means that the kernel of T has to just have 0 in it, right? Because to have a non-zero vector in the kernel would be to say you have a 0 eigenvector, which leads to problems. So we can see that the kernel of T should be 0. If the kernel of T is 0, that means T is 1 to 1. But we're in the context of a mapping from V to V. So if the mapping is 1 to 1, it's also automatically onto, right? Because we have this theorem for linear transformations going from a vector space of the same dimension to the same dimension. So since it's 1 to 1 and onto and linear, it's a linear bijection. It's an invertible map. It's an isomorphism. Now I just argued a little bit more calculationally. I said, well, this is its matrix. Since the determinant of that matrix is 6, it's not equal to 0. Therefore, the inverse matrix exists. And if the inverse matrix of a transformation exists with respect to some choice of basis, it follows that the inverse transformation exists. And the inverse transformation existing means that T is an isomorphism, because an isomorphism is a linear map with an inverse, which is also linear, right? So. Now, this is the one I was most vague of all my grading. I was most vague here. But here are the different cases. As I've broken them up, So like, if I want, what are different possible, like what's, basically the question is, what are different ways that a linear, a transformation in 3 dimensions can kind of break down in terms of its eigen, or its generalized, or eigen decomposition, so to speak. It's Jordan, what are possible Jordan forms, what are possible real Jordan forms. And so one possibility, of course, is that you have distinct eigenvalues, which is to say that the matrix is just plain old real diagonalizable. And a follow-up question that I could have tacked on here is, in each one of these cases, comment whether or not the transformation is real diagonalizable, or whether it's complex diagonalizable, if we look at the complexification of the map. So in the first case, it's both real and complex diagonalizable. In case 1, I mean, its Jordan form is this diagonal matrix. Great. And the minimal polynomial is equal to the characteristic polynomial in this case. The next case, we've got a root. So the other thing I forgot to write in my solution is I'm assuming that lambda 1, lambda 2, and lambda 3 are distinct. Oh, I guess I said it here, but it'd be good if I said that. So here, if I have a repeated root, then I can either have the case that the minimal polynomial is split linear. When the minimal polynomial is split linear, which means it's a product of linear factors not repeated, that means that the transformation or the matrix is diagonalizable. So correspondingly, the Jordan form would just be this diagonal where I've got the algebraic multiplicity equal to the, well, excuse me, algebraic multiplicity of lambda 2 is 2. Hey.
Sorry, this is really important.
Oh, okay. That's fine. Fine. I thought there was more than one person that just left, right?
Someone went to the restroom.
Oh, okay. So it's just a coincidence. All right. I was like, is there some kind of like party I'm missing or something? I mean, you know. Oh, parties. Yes. Oh, we'll leave it up. If they come back, they come back. If they don't, it still doesn't matter. It's just top hat. It's not something important like, I don't know, walking your dog, shopping for groceries at Walmart. Like, what's more important than top hat? What? Reading? Breathing. Breathing is very important, though. Try not breathing for like 10 seconds, half a minute. Some of you 4 minutes. It's bad, right? When we want an example of something that's less important than top hat, we need to look for much more frivolous things, like convocation. Now you're trying to make me edit this. Oh, man, that's funny. All right. Anyway, think of the most useless, boring possible thing. It's that thing. All right. Okay, so I did not say that. Let's see here. But anyway, so in this case, it would be diagonalizable. See, and the Jordan form is a diagonal matrix with the eigenvalues down the diagonal. It's also complex. Anytime a matrix or a transformation is real diagonalizable, that means its complexification or itself is complex diagonalizable. Anytime you have real diagonalizable, you automatically have complex diagonalizable. This one here would be the case that we have a Jordan block, right? Both of these have the same characteristic polynomial, but this one has a, this one has the same, the minimum polynomial is equal to the characteristic polynomial in this case. This corresponds to the fact that the algebraic multiplicity of lambda 2 is equal to the geometric multiplicity of lambda 2 as it happens here. All right. What's the third case? Well, we could have the eigenvalue three-peated, right? Just a triple eigenvalue. And in that case, there are actually 3 separate Jordan forms that are possible for a three-peated eigenvalue. It could still be diagonalizable. It's just that you got lambda, lambda, lambda down the diagonal like that. That's one possibility. For example, the identity matrix in 3 dimensions is like this. If I just take A equals to I, that has eigenvalues 1, 1, and 1. And everything's an eigenvector with eigenvalue 1 for the identity matrix. Another possibility would be that the minimal polynomial is just x minus lambda squared. that would mean that you've got two eigenvectors, just two linearly independent eigenvectors. Your eigenspace has dimension 2, but there's something missing because we're in 3 dimensions, right? And so that's accounted for by the generalized eigenvector of order 2, which you need to complete the chain, which makes this block here. Then the third possibility in this case 3 is that we only have one eigenvector, and we need a generalized eigenvector order 2 and also order 3 corresponding to this block. And so that's the other Jordan. That's a Jordan 3 block. All right, what's the other thing? How else could a cubic polynomial factor over the reals? Right? We either have distinct real factors, we have a repeated real factor, we have a three-peated real factor. But the other thing that could happen is it could be that the quadratic that you split off, right? There always has to be at least one eigenvector, right, for a cubic, because any real polynomial has at least one 0, which means that any linear transformation on a three-dimensional vector space always has an eigenvector, because it has a cubic characteristic equation which always has at least one solution. There's always at least one eigenvector for a linear transformation on three-dimensional space. That is not true for a two-dimensional space or a four-dimensional space or any even-dimensional space. There doesn't have to exist an eigenvector. Just that's a quirk of like even-order equations, right? If you have an even-order equation, you don't necessarily have to have a solution. Odd-order equations have to have solutions because of like calculus 1. If we look at the sign, the polynomial which defines the equation has to shift from positive to negative or vice versa as you go over sufficiently larger or positive or negative values of x. The intermediate value theorem says it has to cross 0 somewhere. You only get that argument for odd dimensions, not for even, though. And we actually saw that for the two-dimensional case. We saw an example. Rotation matrices have complex eigenvalues usually, right? Well, actually imaginary ones. Anyway, here's the other case. So we have complex eigenvalue, alpha plus or minus I beta, right? So in this case, this actually doesn't have a plain Jane Jordan form, but it does have the real Jordan form, which has got a lambda and then an alpha plus I beta block, which I think I called RJ2 alpha plus I beta. I can't remember my notation. Is that what I did this semester? RJ2? Okay. I actually think I've done that 2 years in a row now, but I keep doubting my notation. But anyway, at some point I'll actually put it in the notes if I wasn't so lazy. Okay, so there you go. That's the real Jordan form in this case. This matrix is not real diagonalizable. However, it is complex diagonalizable. Not that I asked about it in your quiz. I'm just adding an interesting discussion onto this. So as far as I can cipher, those are the possibilities, right? This is an easier version of what homework problem? Yeah. The one I did in the help session is the good answer to that. I think my solution in the help center may be better than my solution in the actual solution to mission. Yes.
Yes. It was that one.
We don't want calculus 2, right? Yeah.
I'd rather take that test.
Oh.
No. Give me linear. Calc 2.
Apparently they like Calc 2.
Yeah, but currently in our current state, I probably do about equivalent on it.
Let's see here.
You're gonna pull up math 321 test 3?
321 test 3. Where was that?
I don't know. I'm asking you.
Oh, well that just means we'll have a test for
I don't think I've written it. So yeah.
He was hopeful.
Let's see here. Do you guys have any questions about mission 9? Since we have some time here. 157, huh?
Yeah, that's a good one.
Well, I did not say
Oh, not that hard.
that.
Sorry.
I didn't say I wouldn't put something on the matrix exponential test. I said if I put something on the test, it would be not as hard as 157. So a good question to ask would be, so what would be hard enough to be on the test, but not as hard as 157, right?
So what would be?
I already asked. You can't. I already asked that question. You can't ask it. It's too late. I've already asked. I've already asked it. It can't be asked. Different question. An interesting one is something like if we do j equal to 0. Here, I'll do 1, 1, 0 like that. Calculate e to the tj. It's kind of a fun problem. Use cosh t and sinh t to simplify answer. So something like this, it may be that what I'm trying to get you to do is just calculate a few powers of the matrix. So like, what's j squared? In fact, it's not unlikely that I have an A, B, C in this question, and like part A or B is calculate j to the power k as like a, you know, a starting point. But I'm going to be lazy and just state it like this and show you how to do it. Yeah. Oh, wait, but that's the identity. Aha. So apparently, j cubed is what? J, right? What's j to the fourth? It's that, yeah, it's j squared, it's II. I, yeah. All right, let me summarize this. J to the power 2k equals the identity matrix, and j to the power 2k plus 1 is equal to j, right? 4k equals to 0, 1, 2, and so forth and so on. So if I calculate e to the tj, that is the sum, n equals 0 to infinity, of tj to the power n over n factorial, right? By definition. That's the matrix exponential's definition. That was the main thing I wanted you to learn in problem 157 was this definition, right? I probably would state this again on the test question. I mean, but me stating it and you being comfortable with it are two slightly separate things, aren't they? Let's see here. N equals 0. Let's see here. T to the n over n factorial j to the n, right? So by properties of matrix and scalar multiplication, if we have a scalar t times j raised to the n power, that's the same as t to the n times j to the n, right? And then I need a calculus 2 trick. The calculus 2 trick I want is to break this into the sum of evens. So if n is even, I can write it as 2k. Plus odds, right? Because that's just a way of partitioning all integers, positive integers into, well, non-negative integers into even and odds. Right? Now, you could still find your way to a solution here not using the sigma notation, using the plus dot dot notation if you kept about, I don't know, about 6 terms or so. It probably should be enough to see the pattern. But I'm using the sigma notation because this is one of those things you're supposed to gain some familiarity and comfort with in Calc 2. But I know that my thinking is wishful, so I'm trying to teach it to you now. Let's see here, k equals 0 to infinity, t to the 2k over 2k plus 1, plus 2k factorial, rather. Goodness gracious. And this j to the 2k is really what? That I. So I'll just factor that out. Because it's the same on every single term, I can factor it out of the series. And likewise over here, I can factor the j out of that series. Right? But what are we looking at? That's hyperbolic cosine of t times I plus hyperbolic sine of t times j. So sometimes you can calculate the matrix exponential just through direct computation. Another example, I could give you a is equal to 0, 1, 0, 1, 0, 0. Like that. And it's not hard to calculate e to the ta for this either. The thing about this a is it's nilpotent order 3. So like a cubed is 0. A squared is what? Right. And so this is literally, and that's the identity matrix. So this is literally 1, 1, 1. T. And so in short, what we got here is 1 t, 1/2 t squared, 0, 1, t, 0, 0, 1. So calculating the matrix exponential doesn't have to be hard. It can just be a short problem about calculating powers of matrices and interpreting a formula. Yeah. Which is why it doesn't make a terrible question for a linear algebra final, because the ability to calculate this sort of thing indicates that you've reached the sort of maturity that I hope for my students to have when they leave here in terms of matrix computation. How can I make this problem harder but not impossible? What's that? How about I don't? This is hard enough.
Yeah.
Mm. It'd still be on test 3. Well, I'm not, see, but I'm bound by other constraints, which is it's not supposed to be harder than problem 157. But, you know, just one part of problem 157 is not harder than 157, right? Like, if I just ask part A, it's not as hard as A, B, C, D. Think about it.
Sure, probably still wouldn't be able to do it.
Let's look at, anyway, what I was getting at was, if I give you something like, I'll make it a little bit simpler. If I did like 2, 1, 0, 2 like that, if you wanted to calculate the matrix exponential, something like that, if I call this A, what I do is I rewrite that as like t a minus 2i plus 2i, like that. And so that gives me e to the 2it, e to the t times a minus 2i. But a to the minus 2i, so this gives me e to the 2t times I. Grief. And this one just gives me I plus t times 0, 1, 0, 0. Because a minus 2i here is this guy. So like only the first two terms in the matrix exponential survive. And what I'm doing with that e to the 2it is really part A in problem 157. Right? Part A was realizing that if I have a diagonal matrix and I take the matrix exponential of a diagonal matrix, I get the diagonal of the exponentials of the end, like that. Really, what I just did in red here is a 2x2 version of part B. So I realized that my matrix has two pieces. It's got the diagonal piece and the nilpotent piece. And I just exponentiated them separately using part A. This is the diagonal piece. That give me exponentials on the diagonal. And then the other piece, the nilpotent piece, the a minus 2i, which is this again, we just get that part A of 157 style, just first two terms. If it's nilpotent order 3, you get out to quadratic. If you had nilpotent of order 4, it would go out to cubic and so forth. But well, part C is just fun.
The bathroom, it sounded like they were sharpening knives or like,
They're-
have it blacked out in the part of the floor you can see out.
Must be a psychology class.
It's they're playing Twister or something. I mean, what do they got? I don't know what's going on there. It's like, the matrix exponential is a pimp. I hadn't noticed that until just now. I haven't done many of these explicitly in class. Maybe none. I don't know. I've at least told you to watch a video where it's done. But are you guys all comfortable with the least squares question? It's clear what to do. I saw one person say otherwise, at least. So let me just talk about it momentarily. The procedure is very simple. Once we know what we're trying to model, we write down a linear equation for that model, plug in the data. Now, the reason it's all one is it's always plus C2. So like it's C1 plus C2, 2C1 plus C2, 3C1 plus C2. It's like when you look at a linear, it's always C2. There's no dependence on X. It's always going to be C2, 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 C. As it rhymes with Gary Busey. But I don't know. I'm just trying to push down my excitement over Taylor Swift dropping a new single at midnight last night. It's all I can do to contain myself.
Are you like actually excited about it?
Oh, I'm really excited.
Taylor Swift got together to sing?
Yes, they did.
This is going to be the greatest ever existed.
Why did I hijack my own class? I don't know. What's wrong with me? Okay, so anyway, what I was getting to in the last one was we write down the linear equation and then multiply by the transpose of the matrix that converts it into the so-called normal equations. The solutions to that will be the best approximate solution to your overdetermined system. The other thing is for a quadratic form, I hope you guys are all ready to write the matrix for a quadratic form. We want it to be symmetric. Pay mind to the fact that you have to half the coefficient of xy. Make sure you've made clear in your mind where, if it's a three-dimensional one, where xy goes versus where xz goes, versus where yz goes. And also, something you don't want to lose points on because it's easy. Eigenvalues, you got to be careful calculating eigenvalues. As a general point of order, when you're doing an eigenvector calculation on the test, if you get through it and you find that 0 is the only eigenvector, what this means is very simple. It means that you didn't actually have an eigenvalue. If you've done the eigenvector calculation correctly and the only thing you get is the 0 vector, that means your eigenvalue is a lie. Right? Because if it is an actual honest-to-goodness eigenvalue, you will find an infinity of solutions, at least one eigenvector, possibly more. Excuse me, always infinitely many, that there could be like more than one independent eigenvector, right? The basis, if the geometric multiplicity of that eigenvalue is larger than 1. How do you find, and by the way, just because you find, if you have a symmetric matrix, especially if it's got a repeated eigenvalue, you find eigenvectors, they don't automatically come out orthonormalized. Like the real spectral theorem doesn't say that they're automatically orthonormalized. It says that there exists an orthonormalized eigenbasis. So if you have a quadratic form with a repeated eigenvalue, it might be that you still have to like Gram-Schmidt on the repeated eigenspace. This is too low dimensional to see it, but like these are automatically going to be perpendicular as soon as you solve them, and you just have to normalize them to get your orthonormal basis. Yep.
Could you, if you wanted to, or it doesn't work, could you orthonormalize it before you did the eigenvalues?
I don't think so. No, no, not that I know of. Something I didn't talk about, and it's a little bit past where the course got to, is, in fact, with a quadratic form, you can always change the basis so that the formula becomes just a sum of coordinates squared minus a sum of minus coordinates squared plus zeros. Like there's a choice of basis where the matrix of the quadratic form just looks like 1, 1, 1, 1, 1, and then minus 1, minus 1, minus 1, minus 1, and then zeros with zeros elsewhere. This is called Sylvester's law of inertia. But again, we didn't get to it. All right. So this one's a good example in terms of, finding the matrix, something more, a little bit more substantive, because you got to think about this xz gives me a 2 here and here, right? That 4yz puts these 2's here and here. The 8xy is this 4 and 4, right? So a lot of times I like to simplify the computational burden of a 3x3 or a 4x4 problem by like telling you something like, this vector is very interesting. What does that probably mean? Probably means you should take that vector and multiply it on the matrix and see that you get back a multiple of the vector. Probably that's an eigenvector, and you need to figure out what the eigenvalue is. I might even tell you, notice that a times this vector is equal to 3 times that vector, right? If I do something like that, that tells you that lambda minus 3 is a factor of the characteristic equation. So giving you information like that, and then like partial information, you should be like thinking about how can I use that kind of partial information to simplify my algebra. If I know that an eigenvalue exists, I know that I can factor that factor out in the characteristic equation. That's something, helpful hint. Let's see here. So as we discussed, to find minimums and maximums of functions of several variables, we do what? We look for critical points and then analyze the eigenvalues of the Hessian. If this problem appeared on the test or final, it would come with a lot of language. I would remind you what critical points were. I would calculate partial derivatives for you if you were stuck on it, because
I think you should.
put one like this on the test. Yeah.
Wait, you calculated our partial derivatives?
If you forgot how, yes, I would.
Oh, I forget that.
None of you need me to do that, though. None of you can actually ask me to do it. I'm just saying I would if it was helpful to you.
Still check. This too, I feel like it's
I will double check your partial derivatives if it comes up. Sure, why not? Let's see here. So Zach asked me like 5 minutes ago about problem. Problem 153.
I'm so lost in calculating a joint.
Okay, these really are not that complicated Okay, so 153, I think I'm really using, was it the adjoint problem we were talking about earlier, Nathaniel? In 162, I basically show that T star just transposes the matrix of a linear transformation. So the laziest way to do it is to use 162. Using 162, we learned that the matrix of the adjoint is actually the transpose of the matrix, so it's just straight up that. That is the absolute laziest way to do this problem. But that's not the way I wanted you to do it. I wanted you to do it by the definition, which I gave was this. So you take xy, t of e1 times e1, plus xy with t of e2, e2. Because e1, e2 is an orthonormal basis for R2, right? And so what is t of e1? Well, t of e1 is t of 1, 0 is what? 1, 0, right? And t of e2 is 2, 3, right? So this is xy dot 1, 0, xy dot 2, 3, which is this plus that, which is the same as that. So, I mean, it's just follow the definition. That's it. Now, of course, if it's complex, it's a little bit, fussier, but, and so this one, I actually contrast both ways of thinking. One way is that the adjoint actually has the Hermitian adjoint as the matrix. So like the matrix of T star is the star of the matrix of T. Using that way of thinking, I get this matrix, which gives me that formula. But I could also follow directly from the definition, as in the notes, and calculate the same thing. Again, vector T of the first basis, vector inner product T of the second basis, and just take that linear combination. That's the formula for the adjoint. I'll wrap it up here just a second. I just want to show you the, I'm, probably not all of you got this problem, but, whoa. That was weird. Anyway, so I calculate in this 162, I think it is, that the matrix of S is actually the transpose of the matrix of T. But S is exactly the, S is T star here in this context. It's just the real case. So, okay, anyway. I think I have given you a very, very tilted and bizarrely one-dimensional review for test 3. You should really look back at everything we've done since test 2. Test 3 will not be just about what I did today. It's going to be much more full spectrum and what I talked about in the announcement that I made where I had that list of things. Like, I'll definitely go back and look at that as I'm making your test 3. Do not count yourself out. Everybody here can make an A on test 3 if you just come prepared. It's possible. You can head